Welcome to The Explainer. Today, we're diving into a meticulous, forensic investigation of an aviation disaster that, well, quite frankly, just doesn't add up. We're looking closely at Air India Flight 171. On the surface, the story seems pretty straightforward. But, when we actually start aligning the official reports with the raw, reconstructed data, a massive discrepancy pops up. If you're the kind of person who appreciates uncovering the truth through hard data and structured analysis, you are absolutely in the right place. Let's get into it. Why did you turn it off? I didn't do it. Just take a second to think about those words. That chilling exchange happened in the cockpit literally seconds after takeoff, and those exact words sealed the fate of over 240 people on board. To understand how a totally routine flight turned into such an absolute catastrophe, we have to figure out what on earth prompted that unbelievable exchange.
Section 1, Anatomy of a Disaster.
Okay, so before we can really analyze the weird data anomalies here, let's set the stage and look at the intense physical reality of this specific flight on that fateful day in Ahmedabad. It was hot, like 36 degrees Celsius hot. And in aviation, high heat means thin air. Fewer air molecules literally mean less lift for the wings and, crucially, less oxygen for the engines to burn. Now, combine that thin air with a massive Boeing 787 Dreamliner weighing over 200 tons because it's fully loaded with fuel for a 9-hour flight to London, and you've got a seriously heavy aircraft that's going to need every single inch of that 3,500-meter runway just to generate enough speed to get off the ground. The margins for error here? Razor thin, right from the moment they push back from the gate. So let's walk through the unstoppable momentum of this takeoff sequence chronologically. They hit V1 at 153 knots. If you know aviation, you know V1 is the point of no return. They have to take off because there simply isn't enough runway left to safely abort. Just 2 seconds later, they hit VR at 155 knots, and the nose wheel lifts. The main gear leaves the tarmac, the plane transitions to air mode, and then, completely out of nowhere, an unthinkable system state change happens, which ends in a desperate mayday call. What followed was brutal. It was a second-by-second destruction that lasted just 2.5 seconds. First, the nose gear strikes an incinerator chimney. Then, the tail embeds directly into a student canteen building. The wings shear off against adjacent structures, and it all leads to an immediate catastrophic explosion. But I want you to notice this absolutely crucial detail. Right at the moment of impact, the aircraft was pitched up at an 8-degree angle. This proves without a doubt that the pilots were pulling back on the yoke, fighting with everything they had to climb and clear those buildings right up until the very last millisecond. Section 2, Reconstructing the Flight Path. To really figure out what forced this massive plane out of the sky, independent researchers actually went and built a 1-to-1 scale simulation to challenge the official narrative. It's incredibly fascinating. They took shaky airport security footage, stabilized it frame by frame, and then triangulated the exact location of a pan-tilt-zoom camera sitting on a 15-foot pole. From there, investigators could mathematically reverse engineer the camera's 1-by-2-inch sensor size and focal length. That allowed them to project a perfect 3D virtual environment right over the real-world footage, basically giving us an undeniably accurate frame-by-frame mathematical model of exactly where that plane was.
Section 3, the Timeline Discrepancy.
Okay, let's dive right into this because this is where the raw data completely shatters the official narrative. The friction point is this massive discrepancy. The preliminary official report claims the plane hit a maximum speed of 180 knots, and then, immediately after that, the fuel cutoff switches were engaged. But the raw mathematical simulation data shows something entirely different. It shows the engines being cut at 180 knots, yes, but then the plane somehow continues to accelerate for 5 more seconds, reaching 196 knots. And this brings us to a literal physical impossibility. Inside a jet engine, the moment you cut the fuel, thrust collapses almost instantly. Any high-pressure gases left in the engine, they're flushed out in under a second. There is exactly 0 residual thrust capable of pushing a 200-ton aircraft forward and upward. So, ask yourself, how on earth does a plane keep accelerating for 5 full seconds after the fuel is cut off? Why does the official report claim max speed was hit before the cutoff? This right here is our central mystery.
Section 4, 4 Theories of Failure.
To get to the bottom of this, we're going to put on our detective hats and use a strict process of elimination on those fuel cutoff switches to find the truth. Let's start with theory number 4. This idea proposes that it was just a mechanical failure downstream. Maybe a fuel pump died or a line burst, and the pilots never actually touched the switches in the cockpit. Well, we can confidently debunk that theory right out of the gate. If you look at the plane's wiring diagram, there is a direct data line called the RDC running straight from the physical cockpit switch to the flight recorder. Every single second, it samples the actual mechanical position of that switch, and the black box reported a true signal for cutoff. This isn't some software guessing game, it's a direct mechanical reading. Those physical switches absolutely moved.
So let's move on to theory 3. Could the plane's own computers have cut the fuel without any pilot input? I mean, modern aircraft are basically flying data centers, right?
We can rule this one out too. The system responsible for automated thrust reduction is called TCMA. But here's the thing. TCMA doesn't physically move the cockpit switches. Instead, it closes a high-pressure valve deep inside the engine itself. And once that happens, it cannot be reversed in the air. It actually requires a manual maintenance reset on the ground. Yet flight data shows the AI-171 engines actually restarted later in that short flight. If TCMA had triggered, a mid-air restart would have been physically impossible. Plus, there's absolutely no auto-trip wiring connected to those cockpit switches anyway.
So that leaves us with human interaction. Theory 2 suggests accidental activation. Could a stray hand, maybe a dropped clipboard, or just an uncoordinated movement have bumped both switches into the cutoff position by mistake?
Not a chance. Boeing designed these switches with 3 extremely robust physical safeguards. First, they're spring-loaded, meaning you can't just push them. You have to actively pinch and lift them against spring pressure. Second, they sit behind raised physical guards. And third, they have mechanical base stops. To suggest that an accidental bump somehow perfectly navigated all 3 of these deliberate physical barriers on 2 separate switches, mind you, within a 1-second window, it's wildly, wildly improbable.
And so, by process of elimination, we arrive at the chilling final theory, Theory 1. Someone in that cockpit intentionally pinched, lifted, and pulled both switches to cut the fuel to the engines exactly as the plane was leaving the runway.
Now, early media reports claimed it was mechanically impossible for a human to pull both switches within a 1-second window. But as independent video analysis has explicitly demonstrated, it is definitely possible to do just that. A single, deliberate motion by a human hand can effortlessly pull both switches down within that split-second time frame. The data leaves this as literally the only logical physical explanation remaining.
Section 5. The Final Mysteries.
Now, while we've narrowed down the mechanism of the engine failure, there are still some lingering anomalies in this investigation that desperately demand answers. For instance, a really major talking point in the aftermath of the crash was the landing gear. Footage clearly showed the gear was still down when the plane crashed. A lot of people asked, why didn't the pilots retract it to reduce drag? Well, our simulation data easily solves this one. You see, the standard procedure for retracting the gear requires the pilot monitoring to verify a positive rate of climb, meaning they have to visually confirm the altimeter is rising steadily. But the disaster sequence initiated when the plane was a mere 55 feet off the ground. The engine spooled down so fast that the plane stopped climbing almost immediately. The pilot monitoring literally never had the time or the data to safely make that gear-up call. Then there's the investigation itself, which has its own weird twists. To read the surviving front black box, India's Aircraft Accident Investigation Bureau needed a golden chassis, basically a standard working housing to read the memory module. Astonishingly, they didn't have one. They had to wait to import basic cables and a chassis from the US NTSB. Think about the irony here for a second. A country operating dozens upon dozens of 787 Dreamliners couldn't independently download the data from one of the most common aircraft types in the world. Crazy, right?
And finally, I want to leave you with this powerful provocation. The rear black box and the emergency locator transmitter, the ELT, were located in the tail section. The ELT's only job is to broadcast a signal after a crash. Both of these devices are literally engineered to survive apocalyptic impacts, crushing deep ocean pressure, and extreme fires. Yet, in a relatively low-speed, low-altitude crash into a building, both of these crash-rated devices were utterly destroyed. How is it that the very equipment designed to survive a disaster failed when put to a moderate test? What really happened to the data in the tail of Air India 171? It's a huge question, and it's one that demands an answer.